Hi, everyone. Welcome back to Bufnagle the podcast, where we explore entertaining and enlightening discussions of the adventure of life and all things good. From science and technology to history and philosophy to leadership and success. We hope to give you a better understanding of the world and skills for everyone to pursue their own adventure.
Ladies and gentlemen, welcome back to Bufnagle, the podcast where we talk about all things good in the pursuit of the adventure of life. I'm Harry. I'm joined by Rafe, but it almost feels like we haven't talked in 2 or 3 weeks, and I'm not sure if that's recording's been funky or you've been busy or I've been busy or whatever. But how are you?
Well, I'm great. Thank you. I think we've both been busy, but through the miracle of the interwebs, we are going to experience something that is, okay. So the people on the other side of this recording, those people that are listening to the Buff and avidly and eagerly awaiting this next episode, they just hear it at the regular sequence. But for us, recording, right, maybe not, we may record things in a different sequence than they get posted. And we may put a bunch together or spread them out, and they don't really know because they're hearing it in their time.
That's part of the uniqueness of the Buff.
Yeah, but what's really awesome about this is that's kind of a macrocosm of today's topic.
That's right. Yeah,
which is everything's relative to you is what's going to happen.
But I think what's even more relative is how good our listeners are compared to everybody else's listeners, right?
We have you have to admit we have some of the world's greatest listeners, and they alone, through no work of ours, has made the Buff a global top 10% podcast. As usual, if you are out there, you can reach us at bufnagle@bufnagle.com. Remember to share the love, share the Buff with, you know what? Do it right now. That we'll wait. Hit that there's a little box with an arrow. Send the Buff to someone you love.
You know, I was listening to another podcast, and the two hosts said, you know what? Send this episode to your friend, to your mom, to your friend's mom. Tell everybody to listen.
Yeah, so you can do that. And you don't even have to send the podcast Harry was listening to. You can send this podcast.
That's right.
Remember, share the love, share the Buff. Give us a 5-star. Hit those. You know, I hate to say this is really important, and I don't like leaning with that. But send it on, and your world will become a better place because our world will become a better place. Remember, subscribe, hit the like button, the smiley stars, whatever you need to do to make sure that you are following the Buff. And remember, tell a friend to listen, and you will get a free episode. Harry, we have talked on and off, I think, according to how these episodes are dropping, with other assorted things in between, just to keep everybody on cue here in true Buff nature. Mm-hmm. We've been talking about the nature of light. And this is a thing that I know I wanted to go through for a long time. And this is our 4th episode on the nature of light, and it's getting really wacky. And it will get really wacky. And I think we're going to wrap things up either at the end of this episode or at the end of the 5th episode in a position where you will be like, I'm really glad I don't travel at light speed, is what you will say to yourself.
Yeah. Otherwise, things slow down, frames speed up, and things get stretched and shrunk, compressed, all different kinds of things.
Yeah. Weird things happen, but we will stay away from black holes because that's even another component of this. So last time we discussed light, we were talking about our friend Albert Michelson, who did all sorts of wonderful things for us at the Naval Academy and with other things that he was doing. And he pretty much showed that light goes at 3 times 10 to the 8th meters per second. And it's like 2.99, something like that, but it rounds to one significant digit. It goes faster than you can run. Let's say it that way. 3 times 10 to the 8th meters per second, or 186,300 miles per second. Now, okay, that's reported to 4 significant digits. So how about I say 3 times 10 to the 8th meters per second, or 200,000 miles per second. That's rounded to 1 significant digit in each one. But the other thing is it kind of acts like a wave, but there's always this question: how does this wave work if there's
Through
nothing.
what does it propagate?
Yeah, what's getting waved? And Michelson showed that there was no ether. There was no magic jelly in
God's like, Concord grape. That'll be great for light waves.
light waves in jelly. And light waves will travel through jelly, but they are not carried by the jelly, which is just a remarkable thing. But Michelson showed that there was no ether. There was no ghostly wind. There was no ether. And so what does that mean? Okay, and it's not like light particles are what Newton thought, which were little bullets being shot out of a light photon gun, and that they move relative to the gun out of which they are shot. So it's interesting to understand what does it mean when we talk about speed relative, like with light waves, the speed of the wave is relative to the medium, right? Mm-hmm. So if it's very windy, sound will go faster in that direction than up. It goes faster downwind than upwind. So
it's a standard Doppler effect.
Well, okay. So no.
Yeah, okay. With sound, you can. The waves get. Oh yeah, you're right. The waves get compressed, right? So you're going to hear a higher pitch compared to a lower pitch when they are moving away from you.
Right. When you are moving to or from the source, but they actually are carried on the wind. So it's like an airplane. It's like ground speed relative to air speed. If you are in a plane doing 60 knots downwind and the wind is traveling at 30 knots, you will be moving relative to the ground at 90 knots. But if you're going upwind, you will be only moving at 30 knots relative to the ground because, right, you're moving relative to the air.
A lot of Cessna pilots just don't go anywhere.
We don't go anywhere because it's too windy. Did I tell you I went to a little air show thing?
You did.
Oh, it was great. There was a little mini air show, a little fly-in at our local executive airport, and I ran out there, and it was great fun to see all sorts of little planes. I took your brother-in-law and your little niece, and she thought the airplanes were great fun. We saw an airplane with we saw some warbirds, I guess you would call them, with those, with the mouths on them with the teeth and the eyes, and she thought that was very cool. Anyway, light does not act like an airplane in the wind, although sound acts like sound gets carried on the wind. Light does not. Light moves.
Light doesn't care how fast the wind is.
Yeah, it just goes. And the question is, how do we make this happen? What does this mean? And it took another Albert to figure all this out, and that is none other than Albert Einstein. Okay, so Einstein made his move right around 1900. In 1905, he wrote his first paper on relativity, and relativity is a there's at least three kinds of relativity. Okay, and it's important that we keep track of what they are. Okay, there's Galilean relativity, which is what we're used to, and we'll review all these things. There's special relativity with regard to space and time and how that works, and generally what happens at the speed of light. And then there's general relativity, which is like the speed of light and space and time and gravity, because
all of it.
Yeah, light works with gravity as well. There's a thing. Gravity warps.
Bends around celestial objects.
It is a weird. You have to do very fancy mathematics. Well, not really fancy math. You have to just do mathematics that you're not used to doing. Galilean relativity is the kind that we have talked about before, because Galileo and many others noticed. Michelson noticed the same thing too. That simply the motion of an object in a closed room is insufficient to determine if that closed room is still or moving, right? So you can't just say, well, there's a ball rolling across the floor, therefore the room I'm in is moving or still. You can't say that. You have to have some experience with something on the outside. Okay, so there's nothing that you can measure in the room itself with regard to Newton's laws that determine whether or not your room is stationary or moving at a constant velocity. Now, if it's accelerating, like if it's going around if you're going around
around a curve. Yep.
around a curve, or if you're accelerating, like you are going from stopped to moving, like in an elevator, or stopped to moving in a train car, you can feel. This is kind of like, I look at it, and those of you.
I'm going to just interrupt you real quick, to completely derail your train of thought. We've now taken Andrew on his first elevator ride.
Yeah.
I don't know if the last time you saw a child on his or her first elevator ride, but the idea of going into the box, the doors close, and when the doors open back up, you are no longer in the same place.
Yeah. Did I ever tell you?
The look on his face was, oh my goodness, how did I get here?
Well,
and I was awake the whole time.
We used to tell you that what they did when they closed the doors is that there were people out there that just rearranged all the furniture. And that's
people
why
do that. Those pranks with porta potties. Have you ever seen that?
I have seen things like that. Well, we used to do a thing where,
great prank.
Okay, what do we call him? America's favorite time traveling
ham radio
anesthesiologist. Yeah, we used to go to the hospital with my dad when he would go to see patients, and we'd wander around the hospital, because that was back in the day when you could just wander around. We would we wouldn't go into the ER, but we could, or into the OR and watch those. But you could wander around the halls and talk to the nurses, and we would do that stuff. And I remember one time we were by the elevators, and this lady and her son came in, and then they stood by the elevators and they pushed the button, and we heard the mom say, as the doors were getting ready to close, we heard the mom say, press the number 2, honey. And so the little kid pressed number 2, and the doors closed, and immediately when they closed, we sprinted to the stairs and ran up to the second floor and stood there in the same position on the second floor that we had been on the first floor. All right. And the doors opened up, and the lady kind of did a little, a little, what a head shake,
And what Michelson would have said about that.
Yeah. Michael said, yeah, there's no ether, but we took the stairs. There's no ether, but there are stairs, is what he would have said. The little kid was like, but, and I remember as they were walking down the hall, the mother said, "They took the stairs, dear." I remember that.
Poor kid.
Oh, poor kid. And that mom having to deal with us wandering around the hospital. But so you're in a room, and you can't tell whether that room is moving or standing still, is the whole point.
Unless it's accelerating. And acceleration, we always think of like the accelerator on the car. But if you've taken physics classes, you know that acceleration isn't motion, it's change in motion. Mm-hmm. It's either increasing your rate, or it's decreasing your rate, or it's changing your direction, because velocity is a change in the velocity vector, and velocity has both direction and magnitude.
So because it's a vector. So if that vector changes, then you can tell, but you can't tell if the vector is 0 or non-zero. All you can tell is if it changes. And that's kind of a higher order thing to think about, is you can't determine motion, but you can determine change in motion. And everything in physics is about changes, and that's all about calculus and all that stuff. So to me, it all fits together into this grand picture of Newton and his buddies figuring out the clockwork universe. But anyway, you can't figure that out if you are just in a closed room. So basically, if you are at rest or if you are moving, things are the same as far as the physics that are happening with you there. Okay,
you can all constant velocity.
Yeah, constant.
Zero is also constant velocity.
Zero is constant velocity. You're exactly right. So as long as you are at constant velocity, you can only determine whether you are moving relative to something. Okay, so in a Newtonian sense, we will say that this relativity means that the laws of physics are the same in any uniformly moving room as they are at rest. So whatever happens when you're moving or at rest, it's the same. I mean, you throw the ball up in the air, the ball comes back down, you roll the ball across the floor, it frictions, it slows down, speeds up, does whatever it does. But you can't tell when you're doing that if the boxcar you're in is rolling or if it's sitting still. So from a physics equations and stuff point of view, that means that the same forces produce the same accelerations and so on when the room is at rest or it's constant velocity. That's what it means. The F equals ma's and all those Newtonian laws are still the same regardless of whether you're moving or at rest. Now, of course, this assumes that you have a room that allows you to do what you want to do, which is like there's a grid on the floor and on the walls, and there's, you can measure things with regard to position and time. So you have appropriate rulers and clocks in your room. This is called a frame of reference. It's an X, Y, Z, which are the position coordinates, and then T. It's that four tuple, like we talked about a couple weeks ago. All right. So in this frame of reference, you can determine the X, Y, Z position of all the objects at time T, and no amount of measuring that stuff can determine if that frame is moving or if it's sitting still. Okay, that's the whole basic relativity thing. But I guess they call it begs a question, right? And the question is, what exactly does a frame sitting still, what does that really mean?
Well, it means it's got to be sitting still in reference to something else.
Right. So on Earth, of course, we mean sitting still. We mean relative to objects that are fixed on the surface of the Earth, like the tree and the house, the tree in my front yard or my house or the sidewalk. Those things are fixed, right? But if the reference frame is sitting still relative to me, and I'm like standing on the sidewalk in front of my house, then it makes sense to talk about standing still. But the Earth is actually careening around the sun at some.
That's a good word for it.
It is careening. Your mom and I
the
had
sun's
an
just got it on a lasso and just whipping it around.
And that gets a little complicated because actually there's the Earth is going around in a circle, or not circle, it's an ellipse. Okay, right? Oh, it's a model.
So you're talking to Mom.
Yeah, so I'm talking to Mom, and I used the word careening, and she thought I should have used swerve. So we had a lot of discussion about the difference between careening and swerving. But I will sit with the Earth careening.
I don't think the Earth swerves. A swerve is a temporary adjustment in your direction.
Yeah, and I think
in order to avoid another object.
Yeah, it's generally deliberate, right? But careening kind of implies this out of controlness that you're just you careen down the mountainside, but you swerve to avoid hitting the rabbit.
That's right.
Okay, or to hit the rabbit, whatever you want to do.
Well, it depends if you need dinner or not.
Yes, that's right. That's right. So the Earth's careening around the sun is something like 18 miles a second, or 20 miles per second if we're going to round to one significant digit. All right. So if the Earth is really moving, well, it's moving relative to the sun, right? And so we could just say, well, we'll use the sun as sitting still. Okay, so that'll be our reference point, will be the sun. But it's not true that the sun is sitting still either, because the sun is orbiting the center of the Milky Way galaxy.
Yep.
Right? And so if you go way out into space, way away from our sun and our galaxy, you would see all sorts of things moving around and spinning, and sometimes in the same direction, most of the time the same direction, but sometimes things spin in the other direction. And you could set up like a reference frame, like in the universe, I guess, like out in the middle of empty space.
You just take like a big glass box and
say, yeah, this is okay. So here is 0, right? Here's X equals 0, Y equals 0, Z equals 0. And now I start the clock. Okay. That would be your reference frame. And if you do that and you check Newton's first laws, and right, that make sure that objects moving in a straight line keep going in a straight line if there's no outside force, that's the principle of inertia, right? And that's why it's called an inertial reference frame. All right. And then you set up another frame, right, that is moving at a steady velocity to the first one, and you check to make sure that holds. So now you have two inertial reference frames. Okay. Now, if you do that and they're way out in the middle of Nowhereville space, there's a sign that says "Welcome to Nowheresville," right? But even that can't be there, right? I mean, it's got to be like out in the middle of nowhere.
It keeps moving.
Yeah, it is moving, right? So it's not obvious which of those reference frames is moving relative. Which one is still and which one's moving? I mean, you can say, well, this one here, so this one's fixed, and now I can make another one move alongside it. Well, why can't you just be in the other one and say that the first one's moving? Okay, as long as the inertial laws hold, there's no way to tell which one is still and which one is moving. All you can note is that they are both inertial reference frames, right? And that they are moving relative to each other. Okay, that's relativity. The only the only motion that matters is relative motion. All right. So if we had ether, you could say, well, I'm moving past the ether and you're moving, you could do, but there's no ether. So the only motion that matters is relative motion. Okay. So there's no ether to measure an absolute zero position in the universe. Mm-hmm. So the only kind of motion that matters is relative motion. Okay. So now by the mid 1800s, they were understanding electricity and magnetism, and Maxwell did these Maxwell's equations when he wasn't making the donuts, right? To describe how electricity and magnetism relate to each other. You move a magnet across a wire, you make a current, the current moves, it creates a
field.
Electric field, creates a magnetic field, creates electric field, and this propagates, okay? And his laws lead to this joint interaction of the E and the M fields, and that these propagate at 3 times 10 to the 8th meters per second,
which is being not energy and mass, but electricity and magnetism.
Yes, thank you. Yes, so these two fields are propagating at 3 times 10 to the 8th meters per second, which is exactly the velocity that Michelson had determined for the speed of light. So
strange how that works out.
But it's interesting to note that Maxwell wasn't doing speed of light experiments. He wasn't doing toothed wheels or rotating mirrors or trying to open the lantern
really fast.
Yeah. So he wasn't doing those kinds of experiments. He was working from like first principles of the strengths of electric fields and moving a magnet and measuring those kinds of things. He was working there. And from that, he deduced the speed of these waves in a manner that's consistent with how other researchers had figured out the speed of sound in air by knowing things like the compression components of properties of air. So like if you know things about air, like its density, right? And how the particles kind of, they bounce around, so they don't want to, it's in a box, so it doesn't just drift away. But there's some kind of, there's this properties of gases and things like that. You can figure out how fast the speed of sound will go if you argue from first principles. And Maxwell kind of did that, arguing from E and M. So he argued from one direction, and Michelson comes in from the other direction. They both land on 3 times 10 to the 8th meters per second. And the determination is that light waves must be nothing more than one of these propagating electromagnetic field wave things. That's what light is.
Sure.
So what you see are just certain frequencies of the same thing that radio waves are, and that X-rays are, and cosmic rays, and all of those other things are the same. You just have, your eye can pick them up, which means that, let's just say it this way. When that wave comes, like, you can't see those waves until you see what they produce. You can't see the wave. You can see the action produced by the wave, which to me is a lot like that secondary reasoning of I can't see the motion, but I can only tell when we accelerate. I can't really tell when whether or not we're moving.
I was talking to somebody the other day, and there was this experiment of, is an apple really red until you see it?
Okay.
Right. And the idea is similar to the if a tree falls in the forest, doesn't make any sound.
Yep.
Which is, well, yes, from a sound propagation point of view, yes, it must make a sound. Just because you didn't hear it doesn't mean that it doesn't exist. Right.
Right. Go ahead.
But with the apple being red, well, it's not that the apple isn't red until you see it. The apple is always red because it reflects those particular wavelengths, and it is not red until you view it, because those are the wavelengths that your eye sees.
Well, but this is what's really interesting. So here's the question, and this is actually a foreshadowing of an episode I'm working on that I haven't told you about.
Excellent. Those are my favorite episodes.
Okay.
Usually those episodes are, guess what we're talking about today? Yeah, and I have no script. Well,
this is an argument that goes back to Owen Barfield in the early 1900s. Okay. And he says this. He says, okay, so there's a thunderstorm rolls through, and the rain falls, and then there's and then it moves off to the east. At least it does here. here in North America, the thunderstorm generally moves off to the east, and the sun is setting in the west, and you get this light shining through the raindrops as they're falling, and you see what?
You will see a rainbow.
You'll see a rainbow. Okay. So the question is, where's the rainbow? Okay. Where is the rainbow?
Because it must be. We've talked about this briefly.
Yeah.
Because the rainbow must be viewed in order for it to exist. Because
Right.
you can move to a different location with all the parameters still being the same and not see it.
Right. So the question is, where is it? Well, it's out there where the water is. Is it really? Because if you go out to where it is, it will appear to be far. I mean, so where is it? Okay. So the rainbow exists when your, I'll call it eye-brain system, the system of the
Optical nervous system.
Yeah. So there's this relationship between your retina and your rods and cones and your optic nerve and your perception in your head, that one, those lobes in the back of your head, that when that system detects this collection of wavelengths that produces that image, that's it requires you. The rainbow requires you to be seen. Now, you could argue that, well, somebody else could see it. And I was like, well, but you and I can see the same rainbow. So it's not unique to the person, but it requires a person to bring it into being.
Yes.
Okay. Yeah. And that's a very interesting thing because it's no, I'm not going to say that
now we have suddenly merged and meshed philosophy, theology, and optical physics all into one.
Well, but these are philosophical questions, right?
That's right.
And what's really amazing to me when we think about this is this concept of, I'll call it creation, this understanding of this interaction with the world at times requires humanity to be part of it. Okay, that to me is just mind-boggling. Okay, I'm not going to say that the spectrum wouldn't exist without man, but as a rainbow, as that concept of what we think about as a rainbow, that requires a person to be there to get it. I mean, it's sure the light will be there.
It requires those frequencies to be interpreted.
Yeah. So there's humanity that has to be involved in that, and that's a mind-boggling thing. And it turns out that's exactly where Einstein's going to lead us at about the same time. All right. So Einstein noted that if you apply Galilean relativity to the understanding of the early 1900s, all right, Galilean relativity is that everything that it doesn't matter if you're moving or sitting still, it's all the same in the inertial reference frame. If you're going to apply that to the laws of physics, it needs to apply to all the laws of physics. They must be the same in all inertial reference frames. And that would include Maxwell's equations and the electromagnetic fields and waves, in addition to all those things, just like masses falling and, people throwing cannonballs and all those kinds of things.
Because people just throw cannonballs in their free time.
They do if they're doing experiments. Like I think Galileo dropped some of those things off the Leaning Tower of Pisa to demonstrate that they fall the right way.
Look out below.
Look. Oops. Sorry. All right. So now,
you think he had to get a permit?
Could you imagine what that would like? Okay, I sure hope he didn't need to get a permit or write a grant to do that sort of thing. All right. So Einstein has this demand, okay, that if we're going to have relativity in the Galilean sense, we must also we need to be able to apply Maxwell's laws in there as well. And when we do, it leads to a major consequence. Okay. And that's the big takeaway from all of these episodes on light is that Maxwell says the speed of light is 3 times 10 to the 8th meters per second. Therefore, this needs to apply to any light wave measured in any initial reference frame, right? Any one of them has to travel at 3 times 10 to the 8th meters per second. All right. And that's the whole thing with special relativity is all of these laws are the same in all inertial reference frames. And that means any measurement of the speed of light must yield 3 times 10 to the 8th meters per second. And that's a contrary thing to just what we talked about with the airplane moving with the wind or against the wind, how those speeds add up. It turns out light doesn't behave that way. The propagation, okay, now remember light, we always think about light as like little bullets traveling, but it's not. It's a propagation of a wave that Galileo noted that nothing you could do in your initial reference frame could assist you in determining if you were at rest or moving at constant velocity. In fact, no observation at all helps, even measuring the speed of light across your room. So if you're measuring the speed of light going through your room, that doesn't help either, okay? So this means that this concept of at rest, this point of this 0 point, at rest has no meaning.
It just does it not matter?
Well, you can't say something's at rest. It doesn't have you can be at rest relative to this table, but all that means is that you're traveling at the same velocity as the table, right? So you and I, we can be moving at the same velocity, but we don't know. All we can do is measure that velocity to each other, and if we're moving at the same one, the difference is 0. So there's no relative motion, okay?
Right. Yep. So
there's no inertial reference frame for the universe. There's no fixed. The universe isn't in a box. The universe's inertial reference frame isn't a big gigantic box in which all the other ones take place. There's no way to put a reference frame in the universe. There's no 0 point.
Now, what if you could remove yourself from the universe and look in?
Well, that seems to me like that's a contradiction, because I don't agree with the premise. If you're looking from the outside, where are you? If you're not in the universe,
what if you were outside of space and time?
Well, okay, then you would be a very special being.
I'm trying to bait you here and lead you.
Well, you would be a very special being that maybe would be all-knowing and all completely merciful and completely just. Maybe that's how you would be, something like that. So our friend Fowler, who put together these wonderful notes that we use, says, quote, "Naturally, there can be no ether, no thin, transparent jelly filling space and vibrating with light waves, because if there were, it would provide the natural rest frame and affect the speed of light as measured in other moving inertial reference frames, as discussed above." So the experiments that Morley was doing, or Michelson and Morley were doing to measure the ether, they were doomed from the start. There was no ether to measure. Light was not slowed down by going upstream. Light always travels at the same speed, c, all right, 3 times 10 to the 8th meters per second, all right, every time, no matter how you do it. So this answers the question as to what the speed of light is measured relative to. We've found it's not like sound being measured relative to the underlying medium, and it's not like bullets being shot out of a gun or a light source, like Newton's emitter theory. Light travels at 3 times 10 to the 8th meters per second relative to the observer. Since
who is setting up that inertial reference frame?
He or she or they or whoever, whatever. The people seeing the light are the ones who determine how fast it goes relative to them. It goes at c, 3 times 10 to the 8th, regardless of any velocity between that reference frame and any other reference frame. It's always 3 times 10 to the 8th meters per second. It's not just a good idea. It's the law, as they say, okay? So this is a fundamental finding that changes everything. But not until you start looking at things going really, really, really fast. And we're talking like large fractions
close to light.
Yeah, close to the speed of light. Okay. And you can do all sorts of wonderful things with regard to the speed of light and what this implies by doing some things called thought experiments. Now Einstein didn't actually hop on a light particle and ride it. He didn't have a.
That's what we think.
He didn't have a bicycle traveling at 9/10 the speed of light and turn on a flashlight. He didn't do that. But all you have to do is think these things through, and you can come up with some wonderful conclusions. And we are going to take up a very important one of those questions which is what happens if two people are moving very fast relative to each other and watching clocks in the other reference frame, what happens to them. And we are going to find a very interesting thing about that. And actually, the train cars and train tracks that they ride on are going to be interestingly affected as well. So, but we're going to do that next time we talk about light, Harry, which will either be next week or the week after, depending what happens.
Depending on the buff's schedule in the meantime. That's right.
That's correct. So
yeah, unfortunately we can't change time, right? It's not like we can sit here and say, hey, if you travel really fast, the buff will get there faster.
No, actually, we'll find out that, well, actually, you know what? The buff will still get to you at the same time because the buff travels, essentially at the speed of light.
That's right. So we remind everybody in the meantime to seek the good, live virtuously, and flourish, and enjoy the adventure of life. It's going to be a great day.